All right, so what we're looking at today are some properties of the definite integral, and there are some of them that we've kind of talked about before with antiderivatives, and some of them that are new. So when we're talking about the definite integral, we're talking about the area under the curve. So notice the difference. When these have these limits of integration from a to b, it's representing the area under the curve. So say we wanted the area under the curve of f plus g. So if we added two different functions together. Now this is exactly as expected. It works the same way as it did with antiderivatives. You take the area under the curve of f with respect to x, and then you either add or subtract. Whatever the sign is here, we keep the same sign here. The area under the curve of g from a to b. Okay, so sum and difference rule works the same as the sum and difference rule always has. Whether it's derivatives, antiderivatives, definite integrals, we can split them up into two separate pieces and add or subtract. And then the constant multiple rule, the second one right here, works the same way that a constant multiple rule always has. If you've got a constant right here, this rule says you can take the constant, move it out front, and then worry about taking the area under the curve. So this one actually works really, really well. Like say that we found the area underneath x squared. The area under 2x squared would just be twice the area under x squared. Or the area under 5x squared would just be 5 times the area under x squared. So this one works really well. For this next one, for a is less than b. All right, so starting off with this is important. If a is less than b, if you're trying to find the integral from b to a, so notice it's switched from what you have right here. Normally you're trying to find from a to b because a is on the left. If you want to find the integral from b to a, what you do is you take the opposite of the integral from a to b. Okay, and this one I actually want to make a note on. So this, you're normally integrating from left to right. Like if a is the smaller value, you're integrating from like 1 to 3, or you're integrating from 5 to 10, or whatever. If we switch them and they ask you to integrate from 10 to 5, you take the opposite of the integral from 5 to 10. So integration from right to left rather than left to right makes the integral negative. All right, so if you integrate from right to left, you just make it negative. For a is less than b is less than c. If you want to take the integral from a to c, and this one I've got some space because I'm going to draw a picture, you can take the integral from a to b, because remember here, b is in between a and c, and then you add to that the integral from b to c. And it's very important that it falls in this certain order right here, so I'm going to draw you a picture. So let's say we've got some function, doesn't matter really what it looks like. So say we've got a, b, c, so this part has to hold right here. A has to be on the left, then b, and then c. If we're trying to find this, the area from a to c, that means we want this area right here. From this line to this line, this whole area in here. So you could take the area from a to b, you could take this area right here and then add to it the area from b to c. That's all this is saying. So if for some reason you can't go all the way from a to c with the formulas that you have, you can go from a to b, then add the integral from a or from b to c, and then you get the whole area that way. Okay, next one, the area from a to a. So this one should hopefully make sense. If we use, like this picture would work here, the area from a to a, if I don't move anywhere, then I'm not picking up any area. And so here, the area under the curve would just be 0. Like if I don't have any width at all, here if I go from a to b, my width is whatever I have right here. But if I just go from a to a, I don't have any width. So if my interval doesn't have any width, I can't possibly have any area under the curve. All right, and our last property, the comparison theorem. So if g is always less than f, so I'm going to draw a picture to start off. So, and not always, I guess, from a to b. So say we've got a function g, whatever it is, and then we've got a function f, however it looks, it's up above our function right here. So if g of x is less than or equal to f of x on an interval from a to b, again, it doesn't mean it always has to be lower, it just means it needs to be below it on an integral from a to b. Then what the comparison theorem says is that the integral from a to b of g of x, meaning the area from a to b of g of x, which is represented by that little trapezoid right there, that area is always going to be less than or equal to this area. which that should make sense. If you've got a function f of x, if the function f of x is larger, that means it's going to be taller, means it's going to have more height at any point. And so if a rectangle has more height, it's going to have a larger area if you're looking from the same width from A to B. So it's saying that this area right here that I just highlighted is always going to be less than this area right here if you go all the way underneath f of x, which again should make sense, but it's something that will come into play once we have the need to compare integrals and compare areas under the curve. Okay, so example 5, we're going to pull some of these together. So we've got these 4 different values that we're looking at. We don't know what f is. We don't know what g is. We have no idea which one's larger, which one's smaller. All we know is these distinct areas right here. So underneath f of x from 1 to 3, the area is 9. Underneath g of x from 1 to 3, the area is 4. Underneath f of x from 0 to 1, the area is -2, and then from underneath g of x from 1 to 4, the area is 7. So evaluate these integrals. For f of x, if we want to go all the way from 0 to 3, if we look here, we don't have anything that goes all the way from 0 to 3. First of all, we're only concerned about the f of x ones, so we've got that one and that one. This one goes from 1 to 3, this one goes from 0 to 1, so we get to use this property right here. If we want to go all the way from 0 to 3, we first go from 0 to 1, then go from 1 to 3. So we end up adding those together. So we can do the integral from 0 to 1, and then add to that the integral, or the area, from 1 to 3. Okay, and like I said, we don't need to know what the function is in order to figure out these values. So the area from 0 to 1 is -2. That means not necessarily that the whole function is below the axis at this point, but it means more of the function is below the axis because the negative area takes over. And then plus the integral from 1 to 3 is 9. So again, this doesn't mean that this function is entirely above the x-axis from 1 to 3, but it means it's more so above the x-axis because the positive area took over. So we end up with 7. All right, so the -2 and the 9, we add them together, we get 7. Here, all right, so let's combine these up. So with this one, we need to use a couple of different properties. We're going to use the sum and difference rule, first of all, to split it up into 2 different integrals. And you always keep the same limits of integration. Like if the original one went from 1 to 3, then these should each go from 1 to 3. And then next we have the constant multiple rule. This is property number 2 that says that we can move that 2 out front. So 2 times the integral from 1 to 3. And then same thing, minus this integral that we already had written down. So basically what we're doing is we're trying to rewrite the integral that we're given right here in terms of the integrals that we have up here. So we've got 2 times, and then we know the integral from 1 to 3 is 9. So that gives us 9, minus, and then we're given the integral from 1 to 3 under g, which is 4. So we end up with 18 minus 4, which is 14. Okay, so keep in mind, like I said, we don't need to know what these functions look like. All we need to know is these 4 values right here and how to use our properties. Okay, next one, the integral from 3 to 4. Okay, so this one's a little bit different. This one goes from 1 to 3. This one goes all the way from 1 to 4. So what we're doing is we're actually doing kind of the opposite of this property right here. And let me show you how it's set up. So going all the way from 1 to 4, then only going from 1 to 3, we're actually going to subtract the 2. So we're going to take the area under the curve from 1 to 4. And then since we only want to go from 3 to 4, we're going to subtract the area from 1 to 3. Okay, so let me show you based on a picture. So pretend we only wanted this area right here, just from B to C. We would take the whole area from A to C and then subtract away the area from A to B. And that would leave us just with this sliver that we wanted. So if we just want from 3 to 4, we're going to take all the way from 1 to 4, then subtract away what we get from 1 to 3. So from 1 to 4, the area is 7, minus, and then from 1 to 3, the area is 4. So what it leaves is the area from 3 to 4 is 3. Okay, this one, we get to use property number 3. This is the first time we're trying to integrate from right to left rather than from left to right. So property number 3 tells us if we try to integrate from right to left, we make the integral negative and then switch it back to left to right. Okay, so negative, and then we know the integral from 1 to 4, that's one of the ones that was given to us up here, is 7. Okay, so that one was a pretty quick one. That's just negative 7. All right, so there's a little bit of use of our properties. We are going to look at our very first integral formulas on the next page. Just a few quick and easy ones. All right, so some definite integral formulas that were given to us. The integral of c, we're going to start this off with a picture. So c, remember, is just a constant. So if we've got a function c, just a horizontal line right here, and if we want the definite integral from a to b, remember that means we want the area under the curve. So we saw something like this a couple classes ago. We want this area right here, which as it turns out is just the area of a rectangle. Okay, so the area of a rectangle, it's got a width of b minus a. Whatever these numbers here are, the width is b minus a, and then your height is c. So you end up with c and then times the quantity b minus a. It ends up just being the area of a rectangle. Like I said, the height of this rectangle is c, and the width is whatever b minus a is. If this were 1 and this was 5, the area, or the width would be 4, which is 5 minus 1. Okay, next one. We're going to draw a picture for this one too. X, the area under x. So this is the line y equals x, just a very simple line here. And we're going to start at 0 this time. So starting right here and then ending at b. Okay, so we want this area. Now this area can be given to us as a triangle. Okay, so if we're trying to find the area of a triangle, if this is b, this is an important part, that means this height is b as well. Because the line is y equals x, so whatever value you have for x, you get that same value for y. So the area of a triangle, of course, is 1/2 base times height, which means we've got 1/2 times base. All right, so we end up with 1/2 base squared. That's how we get the area. So if we wanted to go from 0 to 5, we would just plug a 5 in here. If we wanted to go from 0 to 10, we would just plug a 10 in here. So that's 1/2 base squared. All right, so now these next ones I'm just going to give to you. These ones are in the book. And so this one, if we were to draw x squared, it ends up being this formula. 1/3, whoops, not x, b. 1/3 b cubed. This one ends up being 1/4 b to the 4th. Now those might look familiar. I'm hoping they look familiar. We will talk more about them in the next lesson. It's very important to note here, though, that all 3 of these have a lower limit of 0. Has to start at 0 in order for these formulas to work. We will see in the future how you could start it at a different value. But for right now, 0 is our first step, and then you can go to whatever upper limit you want. Okay, so we're going to look at this last example here. We want to evaluate this based on the properties of integrals that we've learned and these definite integral formulas that we've learned so far. Okay, so what we're going to do, first of all, is this piece right here. Following these 3 guidelines, like I just said, we don't know how to start at something like -2. We do know how to start at 0. So if we look back at this property right here, instead of trying to go from -2 to +2, I can split it up. And I'm going to use 0 as kind of that middle ground. Okay, so I'm going to split it up into 2 pieces. I'm going to go from -2 to 0 of this function right here. And then plus, I'll pick up at 0 and go to 2. Okay, so that's the first split I'm going to make, and that's based off one of my properties. Okay, so this one is now good to go, because this one fits in with these patterns perfectly. It has a lower bound of 0. This one does not, but it does have an upper bound of 0. Okay, so I've got this other property, and I'm just going to keep flipping back and forth. We've got this other property that says if we want to integrate in a different order, all we have to do is make the integral negative. Okay, so that's my next step. So next, I want my lower bound here to be 0, so I'm going to flip the bounds. So now I'm going to go from 0 to -2, and all I have to do is make the integral negative in order to make that work. Okay, and then this one doesn't change at all, because this one was good just the way it was. Okay, next thing I'm going to do, I've got a difference in both of these. A difference meaning subtraction, not like they're different. I've got a difference in both of these, so I'm going to use the sum and difference rule to split off into 2 different pieces. So the negative integral from 0 to -2 of 2x cubed, and then minus the negative integral from 0 to -2 of 3x squared. Whoops, I missed my little dx in here, sorry. Then plus, now split these ones up too, from 0 to 2 of 2x cubed, dx. And then because this is negative, I'm going to put minus the integral from 0 to 2 of 3x squared dx. Okay, so we are just about done using our properties. The next thing that we need to do is see I have a 2, a 3, a 2, a 3. I'm going to use the constant multiple rule, and I'm going to move that constant out front. Okay, so here I already had a negative out front. There's going to be a 2 to join it. And the integral from 0 to negative 2 of x cubed dx. Plus, I move the 3 out front. The integral from 0 to negative 2 of x squared dx. Plus, here I move this 2 out front, the integral from 0 to 2 of x cubed. And then minus, here I move the 3 out front, the integral from 0 to 2 of x squared. Okay, so now, finally, these pieces right here, like this piece, all 4 of these main integral pieces fit with these rules that I have up here. So if I want this one, for instance, the integral from 0 to b of x cubed is just 1/4 b to the 4th. So I'm going to use that formula. So negative 2, and then 1/4 times negative 2 to the 4th. Plus, now this one I have a 3, this is an x squared. So if I go from 0 to b of x squared, I follow this formula right here, 1/3 b cubed. Okay, and then plus 2, this one's the x cubed. So I follow this formula right here, 1/4 b to the 4th, and b is the upper limit. So 1/4 2 to the 4th. And then minus 3 times, now this one is the x squared, so 1/3 b cubed, 1/3 times 2 cubed. Whew, okay, so finally we can start to combine these up. So this guy right here, this is a 16, times 1/4 is 4, times negative 2 gives me negative 8, plus, now in here, this gives me negative 8, and then the 3 times 1/3, those cancel each other out, so I have a negative 8, plus, right here I've got 16 times 1/4 is 4, times 2 is 8, not a very good 8, oops, and then minus, here I get 8, and then the 1/3 and 3 cancel each other out, so minus 8. All right, so if we look at this, these guys are going to cancel each other out, one positive, one negative, and I end up with a negative 16. Okay, so that would be my final answer. Now, of course, in the future, we will have a much shortened way of doing this, but you know we have to do the long way first. Don't hate me for that. All right, so we've got this one AP problem down here. We're going to practice that together just so you can see how the properties of definite integrals will pop up on the AP test. But in our future, we are starting to look at the quicker way to do these formulas. All right, so that will be our next lesson.